Welcome to Introduction to Machine Learning. My name is Karim Gazar, your tutor at AWS Machine Learning Scholarship. This session is provided for the reason of explaining some concepts and terms that may not be obvious for the beginners at the first glance. This session covers the first three lessons in the first module, Introduction to Machine Learning. Shall we start? So for the agenda today, we will say why machine learning is the trend now. And then we will talk about supervised versus unsupervised learning. We will explain what modeling is and finish with a recap. So why machine learning now? Machine learning is a modern software development technique and a type of artificial intelligence that enables computers to solve problems by using examples of the real world data. It allows computers to automatically learn and improve from experience without being explicitly programmed to do so. That's the first thing you will read in the lesson. But what does this mean? What is artificial intelligence and how did it all start? Okay, so in the past, computer scientists tried to simulate problems as a graph. So if I have a so represent the problems in the sense of arriving at a destination or solving a maze. So for example, we will represent the target destination as the solution, the edges as the steps or the choices, and other nodes in the graph as an intermediate solution. So let's give an example. Let's say that I am here in the 6th of October city and I want to go to Cairo. The first thing I will do is I will go street, then I will take a bus, take a ticket to the bus, and take another ticket to use the metro until I arrive there. So all these steps represent steps of solving the problem. All these steps can be represented as edges in the graph. This way of solving problems can be generalized to solve other problems like solving puzzles or solving a robot arm control problem by representing intermediate states as nodes in the graph and a solution as one of the leaf nodes, and then let the computer try to search until it finds a good solution. But that have caveats. As the problem gets larger, it gets more complex, and the graph also gets larger. This will require the use of heuristics to guide me through this approach that can take long time. So some other scientists try to introduce something what's called expert systems. Expert systems have a knowledge database that store facts about the world. And there is something called inference engine that takes your questions, get back to the knowledge base, find and deduce new facts from the old known facts and return an answer to you. So what's the problem in this? The problem is that we need experts to get rules from them. For example, I want to simulate an expert doctor. So I already need expert doctors to put their knowledge into the database. I also must take care of the edge cases or weird diseases that may not be obvious or may need more care in giving or answering these questions. This will require a laborious work and a good analysis and a lot of rules that need to be included in this program. And as the problem gets bigger, it gets more complex to maintain such a system. So some other people came with the idea of learning. Why don't I just build a system that can learn and then teaches me these new insights? All I need to do is give him some input, let it learn, and then see the results instead of hard coding the rules. These systems can give insights to me. And these systems will not be only a passive learner that I will encode with the rules that I learn from the world. All of this made machine learning the only game in town. Machine learning is behind the recent advancement in society at all levels. Let's take, for example, autonomous vehicles. In autonomous vehicles, two kinds of machine learning that are vastly used are computer vision and reinforcement learning. A case of computer vision is object detection. Object detection cares about the location, count, and the location, the count, and type of objects in the image. Another case is semantic segmentation. Semantic segmentation classifies each pixel in the image or in the scene. It creates a map of the scene. So as we can see, the cars are colored in blue, pedestrians are colored in red, greens are colored in green. So I have like a legend of the scene. I can understand it better. Both of object detection and semantic segmentation plays a key role in the perception stacks in modern self-driving cars. Let's take another use case. Let's look at reinforcement learning. In reinforcement learning, the algorithms figures out which actions to take in a situation to maximize a reward in the form of a number on the way to reaching a specific goal. Put another way, the machine learns how to arrive or give us the optimal solution for the task at hand through the concept of prizes and punishment. So if my dogs did something good, I will give him like I don't know a bone. If not, I will punish. Okay? So my machine will be treated in this way until it behaves well. So now there are simulators which can simulate environments where the car can be driven virtually, and from accidents, the car will learn until it knows how to drive. This is an amazing concept that is really being deployed and used now in the modern self-driving cars. So let's talk about supervised learning. In supervised learning, every training sample from the dataset has a corresponding label or output value associated with it. So I have like a triangle. This triangle have a color, have a height, have a width. These all are called features. I collect all these features in a table and give it to my machine learning model along with their labels. And after training, my model learns to classify each object that's given to it as an input. The data that I give to my model in the supervised learning can be structured like tables or unstructured like images. For example, I can give it an image of a cat or a dog or a bird and then ask my model to classify each one of the images and give it a label based on the data that I give it at the beginning during the training. Now let's go to unsupervised learning, which may seem amazing to a lot of people. In unsupervised learning, no labels for the training data. A machine learning algorithm tries to learn the underlying patterns or distributions or representation of the given data. So for example, let's say that I have the Mona Lisa photo and I want to figure out the best compact representation of that photo. Okay, so I will make a neural network. We will not cover neural network in this session because it's a very important and deep topic. So we will leave it for another one. Okay, the input and the output of the autoencoder will be the same. So I give it an image and the result is the same image. And with time, this neural network will learn the best representation in the middle, the best compact representation that best describes this data, which can be useful in compressing the data and transferring it across the network. Another good example is the one on the right. The original dataset seems unobvious. Each point can correspond to a user in a website with some features. And I can't, from the first glance, classify or cluster each one of the users. So I give it to a machine learning model. This unsupervised model will classify each user depending, will classify each user and give me the result. So what can this be helpful in? Let's take an example. Let's assume that I have a website and this website have a system that collects user data. Okay, so now I have large amounts of data. I will give this large amount of data to an unsupervised model so it can categorize the users and give a label for each group of them. Depending on the resulting data that I get from my unsupervised model, I can build a supervised one that can classify new user based on their behavior and the previous data that I collected and gave to the unsupervised model. Now I can build a system that can handle each user. So for example, let's say that this man in the middle wearing a nice suit is a businessman that goes to my website and purchases a lot of products. I will just go and offer many discounts that man. Let's assume another user that his behavior may be suspicious. So I may send some warnings to warn him about his behavior. Okay, so what's modeling? Machine learning involves using trained models to generate predictions and detect patterns from data. But what do we mean by modeling? A model is a description of the behavior of something in its environment using math equations. So in the past, physicists will see like pendulum, they will try to understand that pendulum and predict how it will behave. So they will go and bring some differential equations and until they come up with to us with an equation that describes the period of this pendulum. This can be extended to other things in life. Modeling can be used to model the phenomena of, let's say, my store and I sell snow cones. And depending on the temperature, I want to understand how the temperature can affect my sellings. So I collected the data and plotted on a graph, and I tried to draw a line that best fits this data. I tried to draw a mathematical function that takes the input, which is data about the temperature, and predicts output, which is the number of snow cones that I can sell depending on the temperature. If I did that, then I managed to build a model that describes the process that I care about. That is the task of machine learning, is to provide us with models without the need of doing the hard math of differential equations and this kind of stuff. There are different kinds of models. The model that we saw in the snow cone example is called the linear regression because the input is continuous numbers of temperature, and the output is also continuous. Or we can assume it's continuous, although it's not strictly correct because I can't sell like half a snow cone, but there is a continuum of values of snow cones that I can sell each day, depending on the temperature. On the other hand, a logistic regression model answers the question of yes or no, red or blue, a 0 or 1. It just give a class to the input that I have. So for example, I have a picture and I want to know if it's a cat or a dog, and it will, if it's a cat, it will give me one, as we can see in the graph here, one, or it will give me a zero if it's non-cat. Another important kind of models is called the support vector machines. Support vector machines classifies my input data into categories, but it's useful. It gives me what's called a large margin, give me some confidence in my results, and it avoids overfitting. We will try to have a session on support vector machines, as it's a very important topic and used a lot until today. So let's talk about model training. So let's review the steps. First, I need a good amount of data, not too scarce, not very big, but getting more data won't hurt. Okay, so first make sure your data is correct, it's related to the problem and representative to your problem or the categories that you have. Make sure also to remove the outliers or the extreme values. So let's say like collect samples about people, and people are tall, some people are short. I must make sure that the samples that I have contains contains logically acceptable data. So I don't have someone who have 3 meters tall, so who is 3 meters tall, or very short, or this kind of thing. Make sure your data is correct and clean. Then choose a stable model, um, which actually need expertise. So for example, in the last slide, we saw linear models, logistic models, SVMs, and there are also non-linear models like what we will see in later sessions in deep learning. All of them are different kind of models that we will choose depending on the situation. So to get insight into what model to use, we will need to plot the data to get a useful insight into it, and also get a summary statistics of the data that we have. Also choosing a super cost function, which is how we measure the error of our prediction, can really decrease the training time. We will delve into each one of these in detail in upcoming sessions. Now, let's train the model. During the training, the parameters of the model get changed until it's a good fit. So, what does this mean? In the selling snow cones example, our model was just a plain old linear equations with parameters like the slope and the intersection or the intersect. Okay, these two parameters will be modified by our training model algorithm until we get a good fit for the data. Not underfitted, not overfitted. Overfitting means that our model memorizes the input data, the old data, and can't generalize to new data. So if I ask it about something that I provided it before, it will give me the correct answer, but it will not give me a very good answer for the upcoming inputs. So it will not be very useful in the real life. If I want to memorize something, I will just put in memory, put into database, and ask the database. So what did I do? Okay, underfitting is basically to come up with models that actually does not do the job very well. That's underfitting. Okay, now let's validate the model. We will have two kinds of sets. A set that we will call the validation set. This set we will test our model with it until it behaves correctly on this data set first. This will give us a good indication that our model is a good fit for the data and the parameters succeeded in the task. And then after we get our model, we will move it and test it on the test set, which represents an unbiased data. A quick note on the test and validation set. If you have different kinds or categories of input data, please make sure that the percentage, for example, I have 30 image of cats and 30 image of dog. If 50% of my validation set is about cats, make sure that also 50% of your test set is also about cats. Test set should be a good representative of the validation set. So what will happen if this is not the case? What will happen is that you will train your model to behave correctly on the validation set, which will not be representative of the test set. And then you will get unpleasant results when you go and test your model in the real world. So after all that, after following all these steps, you can take your model and unleash the monster and test it into the real world in what's called model inference. In model inference, we use model inference algorithms or use our model to generate predictions about real world data, about new data. So now we can learn more about the real world with our new created model. Thank you.